So this is the conditional probability section 12.4 lesson. It's over conditional probabilities. So let's go ahead and answer these questions on review first, though. So the first question is, what is, it says answer the questions in 1 or 2 words. Describe independent probability. Think a minute. So this is and statements. When we have the and symbol, we're going to multiply. We would return or replace here. So now let's think about dependent probability. So when we talk about dependent probability, that's when we're going to keep something. Again, these are and statements where we have the and symbol and we're going to multiply the two probabilities or multiple probabilities. When we describe mutually exclusive probability, when I talked to my class about this, I used an example for mutual exclusive of having two sets of jerseys, red numbered 1 through 10 and white numbered 11 through 20. Those are mutually exclusive events because they have no overlap. That's when we have or statements. There's our union symbol, and we're going to add, and the only thing we will subtract is when we have overlap, when we have inclusive probability. So the example I gave my students of the inclusive probability was when I have red jerseys numbered 1 through 10 and white jerseys numbered 1 through 10. Here we have overlap in our numbers because we have 2 1s, 2 2s, 2 3s. So when we talk about inclusive, we're talking about the overlap. And we will have to subtract that overlap. We will find the probability of A plus the probability of B, and we will subtract the probability of A and B. Okay, so today we're talking about conditional probability. So this is a measure of the probability of an event given that by assumption, presumption, assertion, or evidence, another event has occurred. So the probability of A given that B has occurred. Now, this statement right here, probability of A given that B has occurred, is equal to the probability of A and B divided by the probability of B. Well, if we were to write this out, this is the probability of A times the probability of B divided by the probability of B. And these two cancel out, so we're really only left with the probability of A. So we're going to talk about how that works in an actual problem in a moment. So let's look at a problem right here. So it says, in Salem, 82% of the households have cable television and internet access, and 90% of the houses have cable television. What is the probability that a house has internet access given that it has cable television? So we're looking for the probability of cable and internet over the probability of cable television, because we want to find out what is the probability the house has internet access given that it has cable television. So the cable television and internet probability is 82%. The probability that cable television is 90%. So what we're going to do is we're going to divide the and statement, the probability of television and internet, or cable and internet, over the probability of television. Now we're going to turn this 82% and this 90% into decimals. So when we do that, we're going to divide 0.82 by 0.90, and that gives us 0.91, and we know that to get the percentage of that, we just multiply that by 100. That gives us 91%. So our next problem here says, at Bay High School, 60% of all students have a car and an iPod, and 70% of all students have a car. What is the probability the student with a car also has an iPod? So here again, we're going to look at our probability of car and iPod over our probability of car, So that's what we're going to do here. So that's going to be 0.6, because again, we're going to convert this to a decimal, and divided by 0.7. That's 0.86, and again, to get it in the percentages, we just multiply that 0.86 by 100 or move the decimal place 2 places to the right. Our next problem, is the check it out example 1. So this one says, and you guys should go ahead and try and do this one and then come back to me. In a neighborhood, 60% of the houses have a garage and a fenced backyard. Given that 80% of the houses in the neighborhood have a garage, what is the probability the house has fenced-in backyard? So this time, again, we're going to talk about the garage and a fence. So we got garage and fence, again, over the one thing, given that 80% of the houses in the neighborhood have a garage. So that's over garage. So that's how we're going to set the problem up. So that means we're going to do 0.6. Again, we're going to change this to a decimal, divided by 0.8. When we do that, we get 0.75, and again, either multiply that by 100 or move the decimal place 2 places to the right. So check it out. Example 2 says 70% of your friends like chocolate, 35% like chocolate and strawberry. What is the percent of those who like chocolate that also like strawberry? Okay, so again, here we're looking at the and. So we're looking at chocolate and strawberry over the percent of just chocolate. So again, that's going to be 0.35 this time, divided by 0.7. So you really have to read this problem because it wasn't in the order that the other one was. That's 0.5, and again, if we multiply that by 100, that's 50%. Okay, so this next part is really what we already talked about. So if the probability of A given B is the probability of A and B are independent, then that's just going to be the probability of A. So that's because the probability of A and B, probability of A, remember that these two are going to cancel out, or no, sorry, given that B has occurred. So that's going to be the probability of B. Whoops, sorry about that. Probability of A and B, given that B has occurred, probability of B. So those two cancel out, we're just left with this. That's how that works. So that's why that works for both of those. Okay, so now let's do some problems, okay? So example 3 is using this table to find the conditional probabilities. Now, the first thing I want to point out to y'all is if you guys have the notes for this, that this value right here is wrong. On your paper, it says 4339. And this value right here is wrong. On your paper, it says 23,305. So you need to fix those two first. And typically when you guys get a table like this, you're not going to have totals. You're going to have to add up this column, get the number down here, add up this column, get the number down here, and also add your rows to get those totals. So you need to do that before you begin the problem. Then we're going to read the problem. So this first problem says an immigrant is from the West. So we need to look at immigrants that are from the West. So immigrants are right here, and our total for immigrants is 11,656. How many of those were from the West? 2,654. So we're going to take this 2,654 and divide it by the 11,656. That's how we're going to do this problem. So when we do that, we get 0.228. That converts to 22.8%. Okay, now let's look at this other one. That someone selected from the South region is an immigrant. Okay, so it says that they're selected from the South. So let's go back here and look at South. So when we're talking about the South here now, we have this total right here. So we have 8285. There's a total of 8285 people from the South. And then again, let's look at this problem. It says immigrants. So how many of the immigrants were from the South? So we got 5042 over 8285. So we're going to do that one again. That gives us 0.609, and that converts to 60.9%. Okay, so I want you guys to go ahead and do the check it out example 4, and then come back to me. So this one says find the probability that someone selected is an immigrant and is from the Midwest. So again, let's go back here and look at the immigrants. So our immigrants here are 11,656, and 2,951 of those are from the Midwest. So that's how we're going to do this problem. We're going to divide the 2,951 by the 11,656. That gives us 0.253, which converts to 25.3%. Okay, now let's look at this next set of problems. So this one says a random survey was conducted to gather information about age and employment status. This table shows the data that was collected. What is the probability that a randomly selected person surveyed has a job given that the person is less than 18 years old? So remember, we're always going to put our given number on the bottom. So if someone's 18 years or older, we got this column right here. So we have 6,000, sorry, less than 18 years old. So that's this column right here. So that's 265. And how many of those people had a job? 20. So we're going to find the probability that someone is less than 18 and has, given that they have a job. So we're going to do 265 in the denominator and 20 in the numerator. So that gives us 0.0755, which is 7.55%. So letter B says, what is the probability that a randomly selected person surveyed has a job given that the person is greater than or equal to 18 years of age? Okay, so on this one again, what is the probability that they have a job when they're 18 or older? So our total for 18 or older is 679. How many of those people have a job? 587. So we're going to divide 587 by 679. That gives us 0.865, and that converts again to 86.5%. All right, let's talk through this last part right here. Are having a job and being 18 or greater independent events? Well, the answer to that is yes, because one does not control the outcome of the other one at all. So now, logically, yes, but not in this survey. So let's talk about how do we find out what the probability is that someone has a job? So if we want to determine how many people have a job, so that's this number right here, 607. So we're going to divide 607 by the total, which is 944. Go ahead and do that and tell me what you get, or we'll figure out what you get. So I got 607 divided by 944 is 64.643. So that's 64.3%. Now, the next question says, what's the probability that they do not have a job? Now, I could take these numbers over these numbers, but this is a not. And anytime we have a not, it is always going to be a dependent event. So this first event was independent, and B was independent, but this is going to be dependent, and B not occurring is going to be dependent. Okay, so let's talk about how we find out if someone does not have a job. So we know that when you have a job and when you don't have a job, those percentages have to add up to be 100%. So we could just subtract 100 minus 64.3. When we do that, we get, hold on a second, 64.3. So that's 35.7%. And again, this is dependent on whether you had a job or not. Okay, so what's the probability that someone is 18 years old or greater? So this time we're going to look at 18 years old or greater, that's 679, and we're going to divide that by our total again. So 679 divided by 944, and that's 71.9%. Now our not, again, is going to be just 100 minus 71.9. So that's going to be 28.1%. And again, our not is a dependent event because it is determined by how many were employed.